Alright, in this video I'm just going to start doing test questions and writing down solutions. Obviously narrating them as I go. So this is a class test from a few years ago. Question 1. The lecturer is growing a plant on the balcony and observes that the rate of change of the height of the plant is proportional to the square root of the current height of the plant. If the plant is 25 centimeters tall when initially measured in late September and is 36 centimeters tall 60 days later, how tall will the plant be 240 days after it was first measured? Alright, and there's a number of hints. We're going to write down an ODE with an unknown parameter, an initial condition. We then solve the ODE to obtain the particular solution involving a parameter. There is enough information, namely that two different heights at two different times, to obtain that parameter. And then we can actually make a prediction, assuming that the growth of the plant remains the same throughout, which, 240 days is, roughly 3/4 of a year. So there's going to be seasonal changes that will affect growth, and we're just going to assume that they don't have much impact. What we've got to extract is that the rate of change of the height is proportional to the square root of the current height. So height is obviously the variable we're interested in as the dependent variable. Time is the independent variable here, and we're given a proportionality relation, which is essentially specifying the entire ODE. So this is Q1 test 1 2021. Let h equal height, t time, and dh dt is proportional to the square root of h. Right? That's h is a function of time. It's the height at any given time, and we're told that the rate of change is proportional to the square root of height. So introducing a proportionality constant alpha, square root h like this, that's our ODE. Now to close this out, we can write down an initial value. So at time 0, when we're counting this from, let's find out what our, I think it's this one. Got multiple versions of the same thing open. Come on, why being turned? Here we go. 25 centimeters tall when initially measured, right? So we've measured this at 25 centimeters. So this forms an IVP, an initial value problem. The ODE is first order. It is not linear because we've got a square root of the dependent variable, but it is separable and autonomous. So let's go ahead and solve this thing. By separation, we write dh on square root h equals alpha dt. We could move the alpha around, but it'll just end up with the t anyway, so we may as well just leave it there. Height is measured in centimeters, I should note that. Time is in days. Okay, so we're integrating. I like to do this integral like this. Rewrite it as the fractional form. Integral of alpha dt is obviously just alpha t. But now we can add 1 to the power, divide by the new power. That's the integral there. I'm going to put my constant of integration on this side, like so, and then say that at t equals 0, h equals 25. Oh my god, what a nice perfect square. That implies that the constant of integration, c, is 10. So now we found that 2 square root h is equal to alpha t plus 10. Or that, right? That's the explicit form for the height of the plant over time. We don't know the alpha at this point. We need to work that out, and we can do that because we've got another measurement of time. So we've got 36 centimeters tall at t equals 60. So if h equals 36 when t equals 60. Let's go back to this form of the equation here because that has the alpha already identified. Right, it's a lot easier to rearrange. We obviously rearrange to get this, so we can back this up to get that and save ourselves a couple of steps. So 2 times 6 equals alpha times 60 plus 10. So 12, we can subtract the 10 from both sides, so we have 2 equals 60 alpha, so alpha equals 1 over 30. Alright, so now we have a completely specified solution for h as a function of time because we know what our alpha is. T over 30 plus 10, it's all divided by 2 and squared. Yeah, I can simplify this if I wanted to. But now I have to answer how tall this plant is after 240 days. T equals 240, h equals 240 over 30 plus 10 divided by 2 squared. That's going to be 8. So that's 18 plus, hang on, what is it? That's 8 plus 10 is 18. Divide by 2 is 9. 9 squared is 81 centimeters. Done. Let's just look over the question again to make sure that we've done everything. Yep. Cool. All right, let's move on to question number 2. Find the particular solution of the following initial value problem and explain each step of your solution carefully in plain language. All right. So this is just straight up ODE. It's pretty easy to solve, but note the marks. In 2021, I was really picky about the explanations. So we're going to have to do a very thorough explanation to get all these 8 marks. So let's go through, let's copy the problem, make sure we copy it correctly. dy dt equals y squared t, y naught equals 1, I think. Yep. Alright, so this is a first order separable. It's not linear. Initial value problem. So we do this step here, TDT. So we shouldn't treat dy dt as a fraction, at least formally. Informally, we get to this step, which is, as I know, an abusive notation. But it does separate, and it is the correct separation. When we integrate, we kind of make everything good again, right? This is kind of meaningless at the moment because of the derivative form, or the form of the derivative. That, however, turns it into an integral equation, and we're good. Both of these integrals are very straightforward. We don't have to do anything. This is add 1 to the power, divide by the new power stuff. The only time that this one's a problem is when it becomes a logarithm at 1 on y, but it's obviously not in this case. So we add 1 to the power, divide by the new power. So when we add 1 to -2, we get -1. So this actually does become a minus. You've got to be careful that you don't accidentally lose that minus sign, right? Sometimes it even helps to write it out as y to the -2. So just so you see it and don't forget it. Put the constant with the t, because that's where it'll end up. We want an expression for y. Sort out minus sign and turn the thing upside down. Right, we've got that. Now, what I would do here is I'd multiply top and bottom by 2. And I'd redefine C. So here, C's gone 2. It'll pick up a 2 and a minus, so it'll do this. So maybe I'll even call this D instead of C, just to be less confusing. Right, Now I have to sub in my initial condition. At t equals 0, y equals 1. So that's 1 equals 2 on D. Oops. So now we can write down our final particular solution like so. Okay, so that's our particular solution in this case. Let's move on to the next one. Let's just check that we've done everything. Yep. Okay, question 3, you're sketching the slope field of this thing, doing an Euler's method. This question has been on this test for about 7 years. Presumably students have shared it. Students keep getting it wrong. All right, so we have dy, was it dy? dx dt equals negative x on t. Okay, and we're asked for the slope field firstly. We're asked for the slope field over a decent range. But what I'm going to do is I'm going to think about how many points I need to represent this thing. All right, so if I choose t equals 0, I've got a problem. T equals 0 means that this problem blows up. Derivative's technically not defined there, but I know that it's going to look like a 1 on x, or a 1 over t in the limit, right? So I know that it's going to asymptote to this line. So I'm going to draw vertical lines down here to represent that. Right, so that's my slope field there. Now, if I choose x equals 0, I get 0 derivative for all t. Except, of course, at the origin, where everything's a little bit nasty. Okay, so that's looking reasonable, right? That's a reasonable representation. This is going to be fairly symmetric, so I'm going to start thinking about what's going on in this quadrant here. If x is 1, t is 1, I've got a slope of minus 1. Okay, if x is 2 and t is 2, then I've got a slope of minus 1. Similarly, I can go up and down this everywhere. Oops. Oh yeah, that's right. So down here I've got a slope of x is minus 1, t is minus 1, minus 1. And so on. Right. Alright, so what happens if x is negative t? So that's this line here. Obviously, that's going to be, the t and the x are going to cancel, but I'm going to have a positive gradient instead. Right, so I can draw that in. Alright, so I might want to draw in some more things around here, 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 and here. Right, that's what I've still got to do. So up here, I've got t quite a bit bigger than, x quite a bit bigger than t. So if say x is 2, t is 1, then I'm going to get a slope of negative 2, right? So it's going to steepen as I move up in x. So I can draw a bit steeper here. I can draw a lot steeper up here. Right? I can only go, because I'm getting closer to this equality line, I've got to it's got to be a bit steeper, but not as steep as these. As I move further away, I can draw a steeper line. Right, so we're going to be drawing things like this. In here, I've got the mirror image. Right, so I can draw something like that. Flip it for down here. Right, I'm just not drawing as many in because I'm just not as interested down there. What happens here? Well, if t is much bigger than x, this gradient's going to flatten out. So I can do something like that, and then I can just kind of repeat the ideas up here. So by symmetry, I can fill in the rest of my diagram. Right, and from this, I can draw some potential solutions in. I can note what's happening to both the function and its derivatives as t gets very, very big or t gets very, very small, or very close to 0. So as t approaches 0, x approaches plus or minus infinity, depending on where you happen to be. T approaches infinity, x tends to 0. Alright, and then that's plus and minus infinity. You can also make comments on what the derivatives are doing. They're essentially as t goes to plus minus infinity, dx dt is also smoothing out. Right, as t goes to 0, right, from any direction, the derivative is also becoming infinitely steep. Right, so I think the initial conditions I had to consider were t equals a half, t equals 1, and they were 1 for both of them. So I'll just check this in a second. Right, which means I'm starting at those 2 dots. Right, so when you start here, you kind of following, remember these lines are tangent always to your flow, so you kind of sketch, so you're joining up the lines. I'm going from the initial point as t increases, right? I'm not going backwards, I'm not letting time decrease, right? So I'm thinking only about an initial value problem where I don't have anything going on up here. That would be time decreasing. As you know, pick a point here, t1. If I went this way, I'd be going from t1 to t half, which is time decreasing. So we don't tend to do that. Of course, if you're just asked to sketch representative solutions, you know, that's a representative solution. Let's see what we're actually asked to do. Sketch on the slope field these particular solutions. Yes, I just did that one. Sweet. Use the slope field to describe in approximately one sentence what happens as t goes to infinity and t tends to 0. Right. So here's this one. This is tricky. Depends on the sign of x. This one's just asymptoting, so that's fine. And that one tells you about the derivative. This is approximately a sentence, I would say. That's certainly what gets you the marks. Okay, recall Euler's method. use Euler's method to approximate the solution of the ODE, this one, if x1 equals 1, and I need to go up to time 2 using this delta. Alright, so the first thing I'm going to do, that's the solution I expect to get. Alright, so from my slope field, I expect my numbers to be going down, and I expect them to go down rapidly and then slowly go down. Alright, that's the kind of behavior I expect to see with my Euler's method. So I've been told delta equals 0.25. I've been told t equals 1, x equals 1 is my starting point. Now my Euler's method formula, x to the n plus 1 equals x n plus delta dx dt evaluated at n. Well, that's just xn plus delta into minus xn over tn, right? And we get that from the ODE up here. Okay, so we need to advance time as well, so we need to write down tn plus 1 equals tn plus delta. And that's everything we need. We now need to just start at t equals 1, advance to t equals 1.25, t equals 1.5, t equals 1.75, and finally t equals 2. So, so this is x naught and t naught. x1 equals x naught plus delta minus x naught on t naught, which is equal to 1 plus 0.25 times minus 1 over 1 equals 0.75. All right, so T2 T1 equals 0.25, right? So this is my x1 T1 solution, right? So I'm just going to keep track of them here. So 1 is there, 1.25 is at 3/4. Right, so x2 equals x1 plus delta minus x1 on t1. So that equals 0.75 plus 0.25 times minus 0.75 over 1.25. Now that's got me running off to a calculator, so I'm not going to pull one up on the screen. I'm just going to do it off screen. So 0.75 divided by 1.25 is 0.6. I should have been able to work that out. Times 1/4, that's 0.15. So I've got 0.75 minus 0.15, which is 0.6. Okay, and the corresponding T2, that's obviously 1.5. Okay, so 1.5, and I'm now down at 0.6. Right, so I've got 2 more points to go. x3 equals 0.6 plus 0.25 times minus 0.6 over 1.5. So back to the old calculator. I'm not even going to bother trying to simplify these. Right, this thing works out, this thing works out to be minus, 0.1. So that's 0.6 minus 0.1. I can do that one in my head. T3 is 1.75. So now I've gotten to a half. Right, and indeed, I went down from 0.25 down, 0.15 down, now I've gone down 0.1. X for 0.5 plus 0.25 times minus 0.5 over 1.75. Okay. Zero 0.5 divided by 1.75 times 0.25, 0.5 minus this quantity. Right, that gives me, this is where the numbers start getting a bit yucky. This is approximately 0.43. Right, you can obviously include more decimal places. The time is now 2, right? So that's where we stop. And that's what our function looks like, which exactly matches what we expected from our slope field. So you don't have to draw this diagram, but it helps keep track of things. I'd be able to tell if I made a mistake, you know, if I was going down here, and then I suddenly shot up here. That's probably wrong. So I like doing it to keep track of any problems. All right. Done that one, didn't have to do any explaining. Using the shape of the slope field or otherwise, make a guess at the solution x of t. Now, I'm looking at this and I reckon that if I guess correctly, I get 1 mark. If I guess incorrectly, I'm going to get 0 marks. So, let's read the rest of the question. Describe approximately in 1 sentence how you could check if a guess is correct. Well, the only way you can check the solution of an analytic problem is to substitute it and see if it works. Right, so we're going to substitute our guess into our solution and see if we get the ODE satisfied, right? There's no way we can use Euler's method or graphical methods or any approximate method to check if our solution is correct or not. That only tells us if our solution is approximately correct. All right, 3, the last part. Attempt to show your guess is correct. So actually do what you were asked to do in the previous part, or what you propose in the previous part. Incidentally, there is another way to do part 2 and 3. You can just solve the ODE. It is a separable first order ODE, and you can bang through the solution and then compare your solution to your guess. That's a perfectly valid answer. Note that even if your guess in the first part is incorrect, you can still answer the last 2 parts for full marks. Right? You can actually, if your guess is incorrect in part I, you can always go back and try again. Right? And if you're not pushed for time, you can actually spend quite a few, make quite a few attempts at guessing the correct solution here. Right, so the solution I'm going to guess, this thing looks like a decay with time, right? It says that x is going with time downwards. So I'm going to just guess. I'm going to keep my guess fairly general, because that's what we like to do. I'm going to say it's parallel or decay like this. A constant in parameter, right? So I've got my constant of integration, and I've got some parameter that I can use to fit. Now, I could substitute in and actually derive an equation for the parameter. I'm going to go 1 step further with my guessing and just say that it's a 1, because I've got something that looks like 1 on t decay. Right, this isn't going fast enough for a squared. Like if I have a look here, 1 this is like 5/4 if you like, and I'm going down to 3/4. So it kind of feels about the right magnitude. If I'm wrong, I can always come back and change it. I'm doing well, Aishigal, thank you. I'm recording a video. A is going to be the constant that comes out in the wash when I actually plug into my ODE. So or so method number 2 is what I'm going to try first. I'm going to sub in dx dt equals minus x on t. Well, I'm just going to try substituting this in. So dx dt equals, differentiate this with respect to t, I get 1 on a on t squared. Now I'm going to get a minus sign out the front of that. So I get this. Now x divided by t and the minus sign in front of it is equal to a, or minus a, t divided by t gives me t squared. So these things are the same and my equation is satisfied. Hooray, I guessed correctly. Now, let's take the alternative approach. Let's solve the ODE. Just for the general solution, it's first order separable. Like so, like so. Integrating this, you get logs on both sides. Now here's a minor wrinkle that often catches students. How do we deal with this minus sign? Well, I want to exponentiate this, but remember if I've got a minus sign here, that's actually an exponent. So I've got a minus 1 here that I can take up using my exponent laws. Now I can exponentiate. Now when I exponentiate this, I get, I may as well write it out properly rather than just sloppily. Right, that's what I get. And so this e to the c, then I've got e to the log, right, so that's absolute value of t minus 1. I can ditch the absolute values by multiplying through by plus and minus, but it's actually an operation on both sides, so that's cool. And I've got x equals e to some constant divided by t, right? If I let e to the c equal a, just for convenience, I've actually recovered my guess. All right, let's say in an alternate universe, x equals e to the negative t, right? It's a decaying function, so it's not unreasonable to guess this. It doesn't have a constant in it, it doesn't have a parameter in it, so it's a bit sketchy as a guess, but let's see. Sub this in to the ODE, dx dt. Well, if I differentiate this, I'm going to get minus e to the minus t. And then if I look at minus x on t, that's equal to minus e to the minus t divided by t. These are not equal. So my guess is incorrect. Alright, here we go. That is the entirety of this test, I believe. Yep, and we're all done.